Walk through this process here. So first of all, it says cans of LaCroix were supposed to contain 355 milliliters. There's some variation of each can because the filling machine is not perfectly precise. An inspector measures the contents in milliliters of 12 randomly selected cans. And this is the results they get. They get the mean of 352.9 of this particular data and the standard deviation of 2.19. Do these data provide convincing evidence that the 0.01 level, the significance level, that the mean amount of LaCroix in all cans filled is less than the target value of 355? All right, so first of all, the first step in is going to be what you'll have in your test is you'll have to do your parameter, and the parameter is just telling me is mu because that's the mean. It's just in words telling me what we are studying and what the mean is. This is 352.9, and so that's going to be, and that is the mean of all of the volume. And so if I said that's the mean in this sample, but mu is the true mean of all LaCroix. So that's why you're going to describe it like this. Okay, for the hypothesis, it's always ho and ha. For ho and ha, you're always has mu for the mean. In a second, we're going to do the other one when it's not means, when we're talking about means. Ho is always equal, and ha is either going to be less than, greater than, or not equal to. The reason we're choosing that it's less than here is because it says right here, is there evidence that it's less than the target? So since 355 is the target, we're seeing if we have evidence, since some of the evidence right here, since my X bar is less than 355, that's some evidence. So we're asking, we know it's less, but is it statistically significantly less? And the significance level is this here where it says 0.01. And that's what we're going to be comparing the p-value to. All right. Okay, so this is a one sample t-test for means. You could say for mu or you could say for means. And the conditions we're going to check is, first of all, is it from a random sample? And secondly, is n greater than 30? If n is not greater than 30, you then have to check to see if the sample data doesn't show strong skewness or outliers. And you can see it doesn't show any strong skewness or outliers. You see the data's right here. And if I were to throw like a blanket over it, it would indeed be about a normal model. So that's all I'm checking. Okay, so the conditions, my mean is 355, my standard deviation is 2.19 over square root of 12. Let's look where I get this from. The 355, remember that's from my hypothesis. That's the ho, the mu equals, that's what that is. And the standard deviation, if you see that I gave you 2.19, and it's over square root of 12, because 12, remember there are 12 of those. So it's going to give you the standard deviation over the square root of n. The general formula is statistic minus parameter divided by standard error, but specifically for this, I'm going to be using t equals x bar minus mu over sx over square root of n. So you have all of these numbers. The x bar is the 352.9. Mu naught, that's just, again, that's whatever in the ho the mu is equal to, and that's 355. The standard error is s over square root of n, and that's where you're getting the 632. And then there's your answer at negative 332. So you can see on this model that we already did, this is the mean, and this is the standard deviation. And we said, is it less than 350? And that's my x bar. And they can draw it like that. Or other way that you can do it, and of course this is still t, and this is degrees of freedom for my degrees of freedom is n minus 1, so it's 12 minus 1, which is 11. Or you can go ahead and put it into a test statistic of 0, negative 1, negative 2, negative 3, and then this is at negative 3.32, which is this one right here. T is negative 3.32. So you could have drawn it, which in class, this is how I drew it, is I drew it with the test statistic. But if you notice, you're going to get the same values. You're going to get the same area shaded. And you're going to get the same. So you're going to get a p-value. The way I do the p-value is go to TCDF, which to get to TCDF on your calculator, you go to Menu, Stat, distribution, TCDF. Now, you have lower bound, upper bound, and degrees of freedom. The lower bound is the most left shaded area, and for this, the most left shaded is all the way to infinity, so I have negative 9999. Upper bound is the most right shaded, and it stops. The shading stops right here at negative 3.32. And the degrees of freedom is going to be n minus 1, and so that's going to be 11, because n is 12. And so when you do this, you get a p-value of 0.004, I believe. And this p-value that they got is just looked up on the chart, and it gives a certain value, but your calculator is actually going to give you an exact value, so you can use that. And since it's less than 0.001, oh wait, hold on a second. I've missed a 0, I believe. I think there's an extra 0 in there. I can look it up for you exactly here in a second. Let's just go ahead and do that. Let's look up our calculator and just do it in the calculator so I can get it exact for you. All right, so let's go ahead and open a calculator page, and I go menu, stat, distribution, TCDF, lower bound negative infinity, upper bound negative 3.32, and the degrees of freedom we said is 11. And it is 0.003. So yeah, I did 34. So I did miss a 0. So this is going to be less than 0.01, which is going to be, we reject, or actually no, I didn't miss it here, 0.004, and that's less than 0.01. I just wasn't thinking right. Or 0.003. I think we're about that. So because it's less than, we reject ho, and that's mean you either go with ho or you go with ha. So we rejected ho, and so we have convincing evidence for, and then this sentence is just ha, that the cans are actually less than 355. And you could just say we have convincing evidence for ha because you already have what ha is right here. You already have it defined. Okay, so this is a one sample t-test for means, and now let's go ahead and do the one proportion z-test for proportion here. So for this one, it says a recently report of elementary schools in Kent claimed that 13%, so that's important, of elementary students typically walk to school. Trey thinks that the proportion is different. That's important. When it says different, that's what I'm going to be using for my ha. It's going to be a not equal to. Different than 13%. Trey surveys a random sample, that's important, of 80 students, that's important, from his school and finds that 17 typically walk to school. Do the data provide convincing evidence that they have different, which means that, again, that's going to be not equal to, proportion of walkers than claimed by the report. Okay, the first thing we're going to do is we're going to state a parameter. And this time, because last time we did mu, because we talked about means, it asked on average values. This now is talking about percentage, so we're using P because P stands for proportion. So P now is the true proportion of just what I'm talking about. So you're in words, you're going to tell me what P equals so that when you use P here, P equals 0.13, you're going to know that I'm talking about that the proportion of students is equal to 13%. That's why I define P, because I'm going to use P in here. All right, so 13% here, you can see because it says the claim. Ho is always my claim. Ho is always my claim. Ho means that's just my initial hypothesis. In physics, you'll often see it'll be H naught, and that's just what I initially believe. And so that's P equals 0.13. And then ha is P is not equal to 0.13. And the reason being is, of course, as it says different. The statistic is given to me as the 17, which I have over here, out of 80. And you can solve that if you want to with a decimal, or you can keep it as a fraction, whichever is more convenient. The significance level is also 0.01 again, just because that's what it gives me. The evidence we do have for ha is that my p hat is 0.2125, and that is not the same as 0.13, so that's some evidence. The question is it significant evidence? So that's what we're going to find out. Remember, it's not equal to, and so it's going to be both sides. The procedure we're about to do is a one sample z-test for p. You'll see I write it as a one prop or one proportion z-test for, and I don't write for p because obviously it is, a p is proportion, but you can write either way. The blue that I had written was correct also. The two conditions, we're going to check random sample, and it is given that it's a random sample, and then my large counts. For large counts for this one, remember, is NP greater than or equal to 10? So we have N is 80, P is, there's my proportion, and that's 17, and that's greater than 10. and then N1 minus P, which is what we have here, and that's 63, and that's greater than or equal to 10. So my conditions are met, so therefore, since my conditions are met, that allows me to go ahead and proceed with the test. I have a mean of 0.13 and a standard deviation of 0.13 times 0.87 over 80. The way I got 0.87 is 1 minus 0.13, and that's 0.87. And I get this for my standard deviation. So the model is going to be P, my mean and my standard deviation, or as I showed you before, you can do a model. Now this is N01. Please notice on our other model it was a T, and so I used T, and that was 11. And the 11, remember, came from degrees of freedom, which was 12 minus 1. But this one is proportion, and so we use a normal model, and we start with this, and it goes out to 3. Okay, so then we're going to find the z-score. To be able to find the z-score, it's the same, if you notice, it's the same general formula for both T and Z, but for my specific formula to find the Z, I use P hat minus P naught, and of course, that's just from the HO. That's what the P equals. And then, of course, that's the same P that we're using down here. So you'll see the 0.13, because I get 0.13, 0.87 over 80, and that's where this comes from here. All right, and I got 2.19. And so 2.19, because it's not equal to, be careful, because HA's not equal to, I've got to remember that it's going to be 2.19 and negative 2.19. So I'm going to be negative 2.19, shaded, and 2.19, shaded. Now I'm going to have to find the p-value. In order to find the p-value, you're going to do normal CDF. We did T-CDF on the other one, but this is normal CDF because it's finding a Z. So that's menu, stat, distribution, normal CDF. The lower bound, so I'm just going to, when I do this, it's only going to do one side of it. All right, but this is going to be the same as this, so then I'll just write it down on both. So it's going to be, lower bound is going to be, I'm just going to do this left side, it's going to be negative infinity. Upper bound is going to be negative 2.19. The mean is 0, and the standard deviation is 1. Now, you guys could use, if you wanted to, you could do this, and you could use this as the mean, this is the standard deviation, and of course, this value that we have at our that's a negative 0.2125. Oops. So either way, and if you did that, that would be lower bound is negative infinity, upper bound is negative 0.2125, the mean and the standard deviation is here. You're going to get the exact same answer no matter what you do. Let's go ahead, and I'm going to put the one that we did in green in my calculator. So let's go ahead to normal CDF, menu, stats, distributions, normal CDF. And I have negative infinity to negative 2.19, and the mean and standard deviation are 0 and 1, and is 0.014. So this here is 0.014, and this here is 0.014. So 0.014 plus 0.014, or times 2, is going to be 0.028. Now, as you see, because the p-value of 0.028 is greater than 0.01, remember that's what I was given in the beginning for my alpha, we fail to reject HO. So now we say we do not have convincing evidence that the school has a different proportion, and which this is just my HA. Okay, I hope that helps, and then just let me know if you have any other questions. Great.